Alright guys, so today we're going to be talking about power series. So what is a power series? Well, power series is going to be a series, as the name says. So let's start at n equals 1, could be at 0 to infinity. In fact, let's start at 0. So we have a constant term. And then we're going to have a constant, Cn, that is going to depend on C. And so far we have a series. That's what we had before. But we're also going to have an x minus a to the n term. So this right here, if the series converges, you're going to be having a function defined for x, where you can plug x in there. So now you went from a series, and now you have a function. But of course, that function will not be defined for every x, because you know you have a series, and the value of the coefficient of the series is depending on x. So that means that it will converge for some values, it may not converge for others. So that brings us to a fact that we're going to state, and that is what or when can this converge. So there's three possibilities. Number one is that it simply diverges for all x. That would be really, really sad. Okay, number two. I gotta be careful because at x equals to a, you're gonna have 0. So let's say at x not equal to a. There. Because, I mean, of course, if you plug x equals to a in there, you're gonna have 0 added infinitely many times. You're still gonna have your 0. No worries. So be a little careful there. Then you could have that it converges for some interval. And I should say for x in some interval, rather. So you have an interval where the series converges, and that's going to be called the interval of convergence. Number three, the other alternative is that it converges for all real x's. So those situations can happen, and we're going to try to figure out how to determine when a function will converge. So let's start with some examples, because that's probably the easiest way to do it. So let's start with some very easy ones. So for example, let's do the sum from n equals 0 to infinity of x, and I wrote n. Well, let's erase. X to the n over n factorial. So this is a very famous function, actually. It's going to be e to the x, but you don't know that yet, supposedly. So let's try to find the radius of convergence and try to find on what interval does this converge. So to find or to determine the convergence, I should have said. So now I have to write more. So to find whether the series converges or diverges, the power series, we will use the ratio test. So we're going to do the ratio test. Remember, we grabbed a row that was going to be the limit as n goes to infinity of the ratio of x to the n plus 1 over n plus 1 factorial, and then divided by, but we're going to multiply times the reciprocal of x to the n factorial. So remember, the ratio test was doing x to the c to the n plus 1 divided by c sub n plus 1 divided by c sub n, but instead of dividing by c sub n, I multiply times its reciprocal, just to save space. And then you notice then that this right here, that n will cancel n of them, and it's just going to leave me with 1x. And then for the n plus 1 factorial, remember that you can write this n plus 1 factorial as n plus 1 times n factorial. And now you see that n factorial cancels, and you have that limit right there. Now x is fixed, so for a fixed x, then this limit here is going to be going to 0. You say, yeah, but x could march out to infinity, but it doesn't matter because you're computing your limit for a fixed x. So once you fix x, n runs out to infinity, this is going to go down to 0. So what does that tell me? Well, that tells me that this limit goes to 0. Therefore, this series, sum from n equals 0 to infinity of x to the n over n, converges, converges, that's the ratio test, right? If you were between, if you got a limit that was less than 1, you were going to converge absolutely. For any value of x. So once you fix a value of x, you take your limit and you find that that converges absolutely. And so if somebody asks you, does it converge? You just say absolutely. All right, so now let's erase this and let's do a few more examples. All right, let's take a look at another example. Let's see how this one goes. So let's try to determine when is this series going to converge. So let's go ahead and do the same thing. We're going to define a row to be the limit as n goes to infinity. We're going to do our ratio test. So we're going to grab the coefficient, including the x to the n, or x minus 2 to the n, and we're going to evaluate it at n plus 1. So if you evaluate n plus 1 at n plus 1, it's going to be n plus 1 plus 1, n plus 2. And then we're going to multiply times the reciprocal of this guy again. Okay? So multiply times n plus 1 over x minus 2 to the n. And again, we're going to try to do any cancellations that we can. And you see you have n here, and you have n plus 1 here. So you're going to be left just with the x minus 2. Let's write it up here. So there's going to be 1 left over. Okay? So we cancel n of them, and we're left with 1. Now here you cannot cancel. Some people will say, well, I have n plus 1 here and n plus 1. No, no, no. You cannot cancel across an addition. So you can only cancel across multiplication. So what that's going to do is you're going to have that the limit as n goes to infinity of the absolute value of x minus 2, you see I pulled this out of the absolute value, times, now n plus 1 and n minus 2 are positive, so I don't really have to put the absolute value, is going to be your row. And then when you compute your limit as n goes to infinity, this is going to be a rational expression of degree 1 and degree 1, both numerator and denominator. So this whole expression in the limit, it's not that they cancel, watch out, in the limit this goes to 1. So then this is going to give me that my x minus 2 is the row. But remember now the ratio test. What do I need from the ratio test? I need the ratio to be strictly less than 1 so that this converges absolutely. Therefore, what I obtain is that the series, let's call it S, or power series, S of x. Let's just write the power series and we know what we're talking about. So the power series converges absolutely or when I should have said, not on, because I still haven't drawn the interval for you, but we'll draw an interval and it's going to be on. But right now it's just when the absolute value of x minus 2 is less than 1. So let's draw that. So you have your real line. Let's do it with this one. And you are going to center it at 2. This is going to be your center. And then to either side of 2, this is a radius. So this interval is going to look like this. You're going to be going from 1 to 3. So from 1 to 3, that's going to be your interval of convergence. So this, you could say, in other words, it converges on, or for, if you will, x in between or in the interval 1 to 3. Now, but what happens at the endpoints? That's something you have to consider term by term. So at x equals to 3, we don't know. Why do we not know? Because at x equals to 3, you plug it in here, 3 minus 2, your row becomes 1. And whenever you have equality, remember that your ratio test tells you that the ratio test is not conclusive. So what I need to do is evaluate it case by case. So at x equals to 3, the series becomes, now I could probably call this s of x. I refused to do it before, now I'm going to do it. So s of 3 will just become the sum from n equals 0 to infinity of, now I'm plugging 3, which is going to be 3 minus 2 is 1. 1 to the n is always going to be 1, over n plus 1. Now you can do this by the limit comparison test. You can do it by the integral test. You can do it however you want. But this is just comparable to a p-series of the form n equals 1, I suppose, to infinity of 1 over n, which diverges. So we will just, I'll just state here that it diverges, but you still would like to be a little bit more specific. Do a limit comparison test. That's the easiest one. Now we're going to evaluate what happens at x equals to negative 3 on the other hand. Negative 3, where did that one come from? 1 is the other endpoint. Just checking if you are paying attention. Yeah, that's what they all say. All right, at x equals to 1. So at x equals to 1, then I evaluate my power series, and I get the sum from n equals 0 to infinity, and I plug 1 in here, from where I get negative 1 to the n over n plus 1. Now notice this is an alternating series. The denominator is decreasing, or sorry, the term an, 1 over n plus 1 is decreasing, and it's going to go down to 0. So it satisfies all the conditions to be, to satisfy the alternating test, but then the alternating series test tells you that it converges. And since the positive one diverged, only conditionally. It doesn't converge absolutely because the absolute values diverge at x equals to 1. All right, guys, so right now we're going to look at this example. There's going to be one that will diverge for every point that is not equal to, or for every number that is not 3. So we have run through 3 different possibilities, or 2 at the moment. 1 where it converged for every real number. 2 where it converged on an interval. And now we're going to do 3 where it's not going to converge. So let's take a look at that. Define your row at the limit as n goes to infinity of x minus 3 to the n plus 1 times n plus 1 factorial all over. Now I did divide because this one is not a fraction, so I don't multiply times the reciprocal, it's the same thing. X minus 3 to the n over n factorial. So just doing the ratio straight up. And this is going to, forgot my other marker. This is going to cancel n of them. And I'm going to have just x minus 3 left over. I should have written it with a different color. Oh well. And now here, whenever I cancel the n plus 1, it's going to give me an n plus 1. When I do n plus 1 factorial over n factorial, just as I did before, I can cancel them and just get n plus 1. This should have been in orange or yellow as you see it. As n goes to infinity, in any case, I get the absolute value of x minus 3 times the limit of n plus 1. Now, this limit is infinite. Doesn't matter how you slice it. This is going out to infinity. Multiply it times whatever you want, unless, of course, x is equal to 3. When x is equal to 3, everything is 0. So this one converges only at one point. So let's say that the series diverges. For all x that is not equal to 3. And so that example is kind of extreme, where there's just one point where it converges. So we went through the 3 possibilities, and then your procedures will always be the same. Start with your ratio test. Then if you get a finite limit, you're going to have an interval of convergence. If the limit is infinite, then you're going to converge just at a point. And if your limit is 0, then you're going to converge for all real numbers. So that's kind of what this whole section will be about. So if you have any questions, you let me know in our session during the week. But if not, we'll wrap it up here. And thank you for watching, and I'll see you in the next one.